In December 2022, in a massive laser facility in California, something happened that scientists had been chasing for over 60 years. For a fraction of a second, a tiny pellet of hydrogen released more energy than was put into it. The output was modest, about enough to boil a kettle, but it proved something monumental: fusion ignition on Earth is real. Fast forward to 2026, and that single experiment has become routine. The National Ignition Facility has now achieved ignition 8 times, with one shot yielding 4 times the input energy. But the real story isn't in a government lab in California. It's happening in warehouses outside Boston, in industrial parks near Munich, and in a startup outside Seattle that's already signed a power deal with Microsoft. To understand why 2026 is the year fusion energy became real, you need to understand what we're trying to do. Fusion is the process that powers the sun smash hydrogen atoms together with enough force that they fuse into helium, releasing enormous energy in the process. A single gram of fusion fuel could produce as much energy as 8 tons of coal, with no carbon emissions and no long-lived radioactive waste. The catch? You need temperatures over 100 million degrees Celsius, hotter than the core of the sun, and you need to hold that plasma stable long enough for the reaction to sustain itself. For decades, this was the joke: fusion is always 30 years away. But in 2026, that punchline is dying. 2 fundamentally different paths have emerged. The first is magnetic confinement, using incredibly powerful magnets to suspend a superheated plasma inside a donut-shaped vessel called a tokamak, or its twisted cousin the Stellarator. The second is inertial confinement, blasting a fuel pellet with the world's most powerful lasers so quickly and symmetrically that it implodes, creating fusion conditions for a nanosecond. Both approaches have achieved net energy gain. Both are now racing toward commercial power plants. And a third path, hybrid approaches like magneto-inertial fusion, is emerging from the wings. Let's start with the laser breakthrough, because it was the first to cross the finish line. The National Ignition Facility at Lawrence Livermore Lab houses 192 of the most powerful laser beams on Earth, all focused onto a target the size of a peppercorn. In December 2022, NIF achieved ignition for the first time, 3.15 megajoules of fusion energy out from 2.05 megajoules of laser energy in. A net gain of 1.5x. The scientific community was stunned. But the real achievement was what came next. By February 2024, a shot produced 5.2 megajoules. By April 2025, the 8th successful ignition hit 8.6 megajoules, more than 4 times the input energy. The record for target gain reached 2.44 in February 2025. This wasn't a one-off. It was a reproducible capability. But here's the problem with laser fusion: it's incredible for science, but horrible for power plants. Each shot destroys the target and takes hours to reload. The lasers themselves are only 1% efficient. To make a power plant, you'd need to fire 10 times per second, not once every few hours. That's why the private sector has largely bet on magnetic fusion instead. And in 2026, that bet is looking very good. If you want to see the future of fusion power, go to Devons, Massachusetts. There, in a former military base turned industrial park, Commonwealth Fusion Systems is assembling SPARC, the most important fusion machine since ITER. SPARC is a tokamak, but with one crucial difference: it uses high-temperature superconducting magnets, or HTS. Traditional tokamaks need massive copper or low-temperature superconducting magnets that consume enormous energy just to stay cold. HTS magnets, made from rare earth barium copper oxide tape, can generate fields of 20 Tesla, strong enough to hold a burning plasma in a machine a fraction of the size. In January 2026, CFS completed its first full-scale HTS magnet for SPARC. SPARC is targeting first plasma in 2026 and net energy by 2027. But CFS isn't stopping at demonstration. They're already designing ARC, a 400-megawatt commercial plant targeting grid connection in the early 2030s. ARC would produce more power than a typical natural gas plant, with zero carbon emissions, running on fuel extracted from seawater. The magnet technology that makes this possible didn't exist 10 years ago. Now it's being manufactured on an assembly line. Meanwhile, The International ITER project in southern France, the original giant tokamak, is still under construction after 20 years and $25 billion. The contrast is stark. The future of fusion is no longer big government projects. It's startups moving at Silicon Valley speed. Tokamaks dominate the headlines, but there's another magnetic design gaining momentum in 2026, the Stellarator. While tokamaks are symmetric donuts, Stellarators are twisted, 3D printed magnets wrapped into shapes so complex that only nuclear physicists and alien spacecraft designers could love them. The advantage: Stellarators are inherently stable. Tokamaks need constant active control to prevent plasma disruptions. Stellarators just work once you can figure out how to build them. For 50 years, building them was the problem. Then AI entered the picture. In January 2026, the Princeton Plasma Physics Laboratory launched Stellar AI, a platform that uses artificial intelligence paired with high-performance computing to design Stellarator magnetic fields in hours instead of months. Generative AI models are now producing Stellarator coil designs that human engineers never considered. Proxima Fusion, a Munich startup that spun out of Germany's Wendelstein 7X Stellarator project, raised €130 million in 2025, the largest private fusion investment in European history, to build the first commercial Stellarator power plant. Their design uses AI-optimized HTS coils in a configuration that maximizes plasma stability while minimizing construction complexity. If tokamaks are the Ferraris of fusion, high-performance but finicky, Stellarators are the Teslas, elegantly engineered, AI-designed, and built for reliability. And then there's the wildcard, Helion Energy, outside Seattle. Helion doesn't use tokamaks, Stellarators, or lasers. They use a magneto-inertial approach, two plasma rings fired at each other and compressed by magnetic fields until they fuse. In 2026, Helion announced they had achieved deuterium-tritium fusion and sustained plasma temperatures of 150 million degrees Celsius. But here's what makes Helion truly different: they're not trying to boil water. Every other fusion design, tokamak, Stellarator, laser, ultimately spins a steam turbine, the same way coal plants have for 130 years. Helion's design converts fusion energy directly to electricity through magnetic field changes, bypassing the steam cycle entirely. This could mean 40% higher efficiency and radically simpler plants. Microsoft has already signed a power purchase agreement with Helion, targeting delivery of fusion electricity to the grid by 2028. Is that timeline realistic? Many physicists are skeptical. But the fact that one of the world's largest companies is willing to bet on it tells you something about where fusion stands in 2026. The conversation has shifted from "can we do it?" to "who gets there first?" The money tells the story. Private fusion companies have raised over $6 billion. Jeff Bezos, Bill Gates, and Sam Altman are all major investors. Altman has said publicly that RE's energy demands can only be met by breakthroughs in fusion. Governments are also accelerating. The US, UK, Germany, Japan, and China have all launched major fusion programs in the last 3 years. China's best tokamak is under construction in Hefei. The UK's STEP program is designing a prototype fusion plant. The Biden administration set a goal of a commercial fusion pilot plant by the mid-2030s, and the Trump administration has maintained that ambition. But the real timeline may be more aggressive. CFS says ARC by early 2030s. Helion says grid power by 2028. Proxima Fusion targets 2035. Even if the most optimistic projections slip, the message is clear: fusion is no longer a science experiment. It's an engineering problem. And engineering problems get solved. The question isn't whether fusion will power the grid. It's which design wins, when it happens, and what it means for a world that desperately needs clean, abundant energy. We're living through the moment fusion stops being a physics problem and becomes an engineering delivery challenge. The laser shots at NIF, the magnets at SPARC, the AI-designed Stellarators in Munich, they all point to the same conclusion. The joke about fusion always being 30 years away? It's not funny anymore. Because this time, the countdown has actually started. If you want to see how this unfolds, subscribe to Future Frame. We cover the technologies that are reshaping what it means to be human. Drop a comment. Do you think fusion will power your home in your lifetime? And as always, thanks for watching.